this video, I'm going to be talking about how to apply the integral test to determine if a series converges or diverges. Suppose you have some infinite series summing up the terms of some sequence an. Suppose it starts at the kth term. Doesn't really matter what term it starts at. But suppose the series satisfies some conditions. Say that you have a function f which agrees with the sequence an at each number starting at k. And suppose f is continuous, f is positive, meaning f of x is non-negative for all x larger than or equal to k. And finally, f is decreasing, which just means that f of a is less than or equal to f of b whenever a is a number bigger than or equal to b, and b is larger than k. So in other words, we have some sequence, which is our infinite series, which is moving along. Looks something like this maybe. These are the terms of the series. And our function f just kind of connects the dots continuously and then starts to decrease. So it's decreasing after some time. In other words, maybe our sequence looks like this. This is the terms of our series going along. And we have a continuous function which just kind of connects the dots on this series. And eventually it just starts to decrease. So it just starts decreasing after this term. This is the kth term. And notice it's always staying positive. So it's decreasing, it's positive, and it's a continuous function that just kind of connects the dots on a series. So now, if you have all three of these conditions satisfied, the integral test says that if the integral starting at k to infinity of f of x converges, then the series starting at k also converges. Also, if the integral starting at k of f of x diverges, then the series also diverges. In other words, the infinite series of an converges if and only if the integral from k to infinity of f of x converges. So in this example, our sequence an is the natural log of n divided by n. We can let our function f be defined by f of x equals ln of x divided by x. We can check that f is continuous for all x bigger than or equal to 1. F is decreasing. We can check that f is decreasing by taking the derivative of f. So in this case, the derivative of f is 1 minus natural log of x divided by x squared. So this will be less than 0 whenever 1 is less than the natural log of x, whenever the numerator is a negative number. So 1 is less than the natural log of x means that x is bigger than e, which is roughly 2.718. So as long as x is bigger than 3, then the derivative of f is less than 0, so f is decreasing. So that's the second condition satisfied. For the third condition, For the third condition, notice that the natural log of x is always bigger than 0 for x bigger than 3, and x squared is also always bigger than 0. So these together mean that f of x is bigger than or equal to 0 for x bigger than 3. So we can apply the integral test using our lower bound as x equals 3. So we need to check that the integral from 3 to infinity of ln of x over x, we need to check if this is converging or diverging. So in order to evaluate this, what we're going to do is take the limit as t approaches infinity and then evaluate the integral from 3 to t. To integrate this, we can do a u substitution with u equals natural log of x and du equals 1 over x. So with this substitution, the integral just becomes u du, which turns into 1/2 of u squared which is 1/2 natural log of x squared, evaluated from 0 to t. Sorry, from 3 to t, because we're starting at 3. So what do we get? We get natural log of t squared minus 1/2 natural log of 3 squared. So this 1/2 natural log of 3 squared is just a finite number. And as t goes to infinity, the natural log of t is going to infinity. So overall, in this limit, we are going to infinity, which means the integral diverges. Therefore, by the integral test, the series starting at n equals 3 to infinity of natural log of n over n also diverges. Now, obviously, even though we're starting at 3, and we determined that this series starting at 3 diverges, we also know that the series starting at 0 must... So we determined that the series of ln of n divided by n starting at n equals 3 diverges. That also means that the series starting at 1, as given in the problem, also diverges. So that completes the problem. In this example, an is the sequence e to the negative n squared, starting at n equals 0. Now we can check that the function f of x equals e to the negative x squared satisfies the 3 conditions for the integral test. First of all, it's continuous. F of x is decreasing because if we take the derivative of e to the negative x squared, we get negative 2x e to the negative x squared, which is always less than 0, since e to the negative x squared is always a positive number, and negative 2x is negative for x is bigger than 0. So the derivative is always less than 0, meaning the function is decreasing. And finally, e to the negative x squared is always less than or equal to 0, meaning f of x is positive. So now, to use the integral test, we would like to integrate e to the negative x squared dx. However, we cannot integrate this function. So what we can do is compare it to a function that we can integrate. Here we can show that this integral is less than the integral of 2x e to the negative x squared, because 2x e to the negative x squared is always bigger than e to the negative x squared. So this integral on the right-hand side is bigger. If we can show that this integral converges, then that would imply, by the comparison test, that the previous integral also converges. So let's evaluate this integral, which is the limit as t approaches infinity of the integral from 0 to t of 2x e to the negative x squared dx. We can make a u substitution. U equals negative x squared, so that du is negative 2x dx. And after our substitution, we get negative e to the u du as the integrand. So evaluating this integral, we get negative e to the u, evaluated from 0 to t. First, let's plug in u equals negative x squared from earlier, and then evaluate from 0 to t. We get negative e to the negative t squared, and when we plug in 0, e to the 0 is just 1. So we're adding 1. Now we're taking the limit as t goes to infinity, and as t goes to infinity, this e to the negative t squared is going to 0 as t goes to infinity. So overall, this is just going to 1 in the limit. So since this integral in red converges, that means that this integral on the left-hand side also converges, since it's smaller than this convergent integral. So by the integral test, the series n equals 0 to infinity of e to the negative n squared converges.